Let us start class 12 mathematics with the notions of relations and functions. We first see the mathematical definition of relations. And this definition starts with two sets, any two sets. Let A and B be two sets. They may or may not be equal, anything is possible. Any subset R of the Cartesian product of A and B, A times B, is called a relation. From A to B. That is, this. So to put it more simply, we have two sets A and B, and a relation from A to B is just any subset of the Cartesian product A times B. Now if you see this definition at first glance, it seems like it has nothing to do with the meaning of the word relation, because this is not what we think of when we think of a relation in real life. For example, you are related to your mother. Where are sets coming into that picture? And why Cartesian products? Why a subset? To make this more clear, we are now going to consider one example. So in this example, let's consider these two sets. Let A be the set consisting of the two integers 1 and 2, and let B consist of the integers 1, 3 and 4. And let R be this relation. One comma 1, 1 comma 3, 1 comma 4 and 2 comma 4. Let us first see if this really is a relation from A to B in the sense of this definition. For that, what should we need? We need R to be a subset of A times B. Is it? For that to happen, the elements in R first of all have to be ordered pairs. Yes, they are ordered pairs. There are 4 ordered pairs. So R has these 4 elements. And the second thing you need to check is that the first coordinates of these ordered pairs all are coming from A. Here the first coordinates are 1 and 2. Yes, they are coming from A. And then the second coordinates of these ordered pairs are all coming from B. The second coordinates are 1, 3 and 4. Yes. So that means this really is a subset of the Cartesian product A times B, and as such R is a legitimate relation from A into B. But still that issue is there, the issue of in exactly what sense are we saying that R is a relation? See, in the sense that R tells us which elements of A are related to which elements of B. Like this, 1 is related to 1, 1 is related to 3 and 1 is also related to 4. So the element 1 of A is related to all the elements of B, 1, 3 as well as 4. The element 2 of A, however, is related only to the element 4 of B. So in that sense, we have a relation. If you look carefully, you can recognize this relation somewhat more compactly like this, the same relation. Note that R is also this. It is the set of all ordered pairs in A times B. So, in tabular notation or roster notation, actually we wrote R, we specified R, but we can also use the set builder notation. In that notation, this is what the relation looks like. Y is divisible by X. Is that really so? Yes, because you see 1, 3 and 4 are, each one of them is divisible by 1. That is why we have these pairs in the relation R. 2 divides 4. 4 is divisible by 2. That is why we have the pair 2, 4 inside that relation. Does 2 divide 1? No. That is why we do not have 2, 1. Similarly, 2 does not divide 3, so you do not have 2, 3 in this relation. So, to put it more compactly, to express it more compactly, the relation R that we have between the elements of A and B is divisibility. Divisibility of the elements of B by elements of A. By that relation, some element of A is related to some element of B, but some element of A is also not related to some element of B. 2, for example, is related to 4 by this relation, and 2 is not related to 3 by this relation. Okay, so in that sense, a subset of A times B is a relation. It relates elements of A to elements of B. Now, it's not necessary, however, that every time you should be able to express the relation in terms of something already known. You can simply have a subset like this. For example, if I call this R1, we can think of another such relation. Again, from same set A to B. Consider this R2 say. R2 say has these elements 1, 3, 1, 4. This is also a legitimate subset of A times B. So, by our definition, it is also a relation. It, however, relates only the element 1 of A to both the elements 3 and 4, and it actually does not relate to any element of B. That's what this second relation is. It looks like divisibility, but it's not the entire divisibility relation. It is something else, okay. But still, by definition, it's a relation. Now, we will primarily see the general definition allows A and B to be different sets, like this example. But we will primarily be interested in those relations where A and B are the same set. That is, you have A times A. Okay, so we will be interested in subsets of the Cartesian product A times A. And two very special relations are there, which are kind of boring also in one sense, and they can actually be defined in this general case itself, where A and B need not be the same. So, let me show you the definition. Let A and B be any sets See, by definition, any subset of the Cartesian product A times B is a relation from A to B. In particular, the empty set is also one such subset. So, it also by definition is a relation, and it relates no element of A to no element of B. Okay, it does not relate anything of A to anything from B because it does not have any ordered pair in it. And that is why this is called the empty relation. From A to B. The other extreme is the subset A times B itself. That is also its own subset. And that relation is called the universal relation. Is called the universal relation from A to B. You can clearly see why they are considered somewhat boring because both of them are extremes. The empty relation doesn't relate anything to anything. The universal relation relates every element of A to every element of B because any such ordered pair is an element of A times B by the definition of Cartesian product. So, mostly we are interested in those relations that lie between these two extremes. For example, that example. Now, there is a language. I am not entirely sure if we should consider this general situation in defining empty and universal relation. In the book, I think this has been considered instead. But regardless, you can have the notion of empty and universal relations in this general case also where A and B need not be the same set. Now, there is a language which simplifies these writings. Let A and B be any sets and R be a relation from A to B. If the ordered pair A comma B belongs to R. You know what this means? This means that the first coordinate small a is an element of A and the second coordinate small b is an element of B, and they form an ordered pair which belongs to R. In other words, R relates A to B. Then we also write another notation to mean the same thing. A or B to mean the same thing, the same statement as this. whatever meaning this one has, this notation has the exact same meaning this notation also has, and we read it as A is related to B by the relation R, or as this, A is R related to B. Or if it's understood what R is, we also simply say A is related to B. Okay. All these statements, A comma B belongs to R, A or B, A is related to B by R, A is R related to B, mean precisely the same thing. If A is not related to B by R, that is, if this ordered pair is not an element of R, then we write this. We write A or B and then strike that R to indicate that R does not relate A to B. In fact, this may look a little strange, but you already have used it. Let me show you in what example you have used it. Oh, but before we do that though, there is another slight language thing. If A is a set and R is a relation from A to itself, from A to A, that means in this case B is equal to A, i.e. R is a subset of the Cartesian product A times A, then we say that R is a relation on A. It's a little cumbersome to keep saying from A to A. Instead, because both the sets are the same, you can have a slightly more compact language. You can express that same thing like this: R is a relation on A or in A. Okay, now we come to that other example, which will tell you that this notation is something you have already used. Sometimes a phrase can describe a relation. Consider the relation is less than. This relation, this phrase tells us about a relation, or is itself a relation on the set of real numbers. What type of relation is it? We know what it is. If R denotes this relation, then this is how you can specify R using the set builder method. Such that X is less than 1, or if you find this phrase a little unnecessary here, we also have that symbol now, our familiar symbol for this less than relation. Okay, so we use this short symbol to mean this same thing. And if you note carefully, this is what we wrote there in that notation, A R B. So that R, the name we have given to this relation, in place of that name we can actually use this symbol. So then this becomes XRY. Okay, so that is where this notation is coming from. This is the general notation, this is the particular notation which you have always used. Okay. Now we are not actually interested in just arbitrary relations on some set A, but we are interested in some particular types of relations. A type of relation where the relation satisfies some properties, because these are some relations which occur frequently in mathematics. They are similar and they occur so frequently that a definition has been given to describe them, to say what type of properties they have. Actually, there are two types of relations which occur frequently in mathematics. One of them is called equivalence relation and the other one is called order relation. This is an example of order relation. We won't study order relations at this level. We will see more about order relations later on. In this text, we are focusing on equivalence relations. So let us now see the definition of an equivalence relation. An equivalence relation includes in it three types of relations simultaneously. Let A be a set and R be a relation on A. Okay, now the things we are going to define next, they only have been defined for relations on a single set. Okay, not from A to B in general, from A to A itself. And let me again remind you what this means. This means that R is a subset of A times A. Reflexive relation. Such a relation R is called reflexive if A comma A belongs to R for all A belonging to A. Not only should you have this, but this part is also very important. This part having the phrase for all. This has to happen for all A in A. If this happens for some elements in A, but maybe it's not true for some other elements, then that's not a reflexive relation. In a reflexive relation, such elements where both the coordinates are equal, they must belong to the relation for all A belonging to A, for every element in the underlying set A on which you have the relation. Note one more thing about this definition. You see, this definition is not telling you that these are the only elements that R has. R may have elements like 1 comma 2 as well. Okay, so besides these elements, R may have something extra, but all these elements have to belong to R. If that happens, then we say that the relation R is reflexive, is a reflexive relation. To make it even more clear, let me present one example. In the middle of the definition itself, I am giving you an example. We should not do it in an exam paper, on exam paper or something like that. Whenever you write a definition in exam, you write the formal definition. You do not inject something extra in between. This is only for our understanding. Suppose A is this set 1, 2, 3, and let R be this relation. I have to show another relation, so let me call it R1. Is R1 reflexive? Yes, because for these three elements, this ordered pair, okay, for each one of them, this ordered pair belongs to R. We have 1 comma 1, we have 2 comma 2, and we have 3 comma 3. It's a different matter that there are extra elements. We do not have anything to do with those extra elements when we are looking for reflexivity. But you see another relation R2 on the same set. So many elements are there from A times A from the Cartesian product in R2. However, R2 is not reflexive because although it has 1 comma 1 and 2 comma 2, but 3 comma 3 is missing. That is why this is not reflexive, this is reflexive. Okay, so that is a reflexive relation. And let us also note one more thing. Simply giving the set for the relation, I mean simply writing what the relation is not enough to decide if it's reflexive. You need to know on which set it is a relation. Otherwise, you cannot say, no, for example, here 3 comma 3 is missing. Okay, you can say that since you have 3 here, so 3 must be present in the underlying set, whatever it is. But say I do not include 3 at all. Say I remove these elements. Okay, I remove these elements entirely and consider the relation to have only these elements. Now you cannot say, if I don't say what A is, you cannot say whether this is reflexive or not. If I remove 3 from the set A, on that set R2 is reflexive. But if I include 3 or something else, then on those sets R2 is not reflexive. So not just the relation R, but the set on which it is a relation, both of them determine reflexivity or its absence. Next comes symmetric relation. These are independent definitions, okay. A symmetric relation need not be reflexive, but it may be reflexive also. They are independent of each other. But they, of course, all of them are about such relations R. R is called symmetric if whenever a comma b belongs to R, in that case we have b comma a also in R. That is, if you have a relation R on the set A where you have some element a comma b, then this other element obtained by interchanging the coordinates must also be in R, and if that happens for every element a comma b in R, then we call R a symmetric relation. You can consider this example where say A is, again let me take 1, 2, 3. And say I consider a relation R1 is R1 symmetric? Yes. For this element 1 comma 1, if you interchange its coordinates, you do not get anything new. You again get 1 comma 1, which already is here. If you consider 1 comma 2 and interchange the coordinates, you get 2 comma 1. Is that also in R1? Yes. If you consider 2 comma 1 and interchange its coordinates, you get 1 comma 2. That is also in R1. And that is why R1 is reflexive. See, these elements do not have anything to do with 3. That's okay. That's not a problem. But let us also see a non-example. That means a relation which is not reflexive. Let me include all these elements and additionally say I write 2 comma 3. This fails to be reflexive. It's okay as far as reflexivity is concerned. Symmetric. Okay, I meant symmetry. As far as symmetry is concerned, these elements do not cause any problem, but this one causes a problem because 3 comma 2 does not belong to R2. So this condition fails for this element. It should not fail for any element, then only it can be symmetric. This is not symmetric. And finally, we have a transitive relation. We call R transitive if whenever this belongs to R and B comma C also belongs to R, we have A comma C in R. If this happens for any two such ordered pairs where A comma B and B comma C both belong to R and A comma C belongs to R as well, then we call R a transitive relation. You can create an example very easily like this. Say we take the same set and you consider this relation on A. 1, 1, 1, 2, 2 1 2 2. Okay, what I mean, in place of a comma b and b comma c, you can consider, say, if you take 1 comma 1, then you can take 1 comma 2, because this and this should be the same. Here we have 1 and 1. So 1 1 and 1 2 both belong to R1, so 1 2 should also belong to R1. Yes, that is already there. If you consider 1 2 and 2 1, then 1 1 should be there. Yes, that is also present. If you consider 2 1 and 1 2, then 2 2 should be present. That is also present. In this way, you will see that any legitimate choice of these two ordered pairs, if you take from this R1, that other ordered pair A comma C also belongs to R1 for this R1, and that is why this is a transitive relation. You can create a non-transitive relation by choosing A comma B and B comma C in R1, but A comma C is not in R1, say. I mean, not in this R1, but in some other relation, say we call it R2. To keep things simple, I can just take this. This is not a transitive relation because 1 comma 3 does not belong to R2. And now we come to the final part of the definition. You do understand, I said moments ago, that a reflexive relation, a symmetric relation and a transitive relation, these are three different definitions actually. None of them depends on the other two. Okay, any relation can be can have any combination of these three things. But if you encountered a relation which has all these three properties, then it's called an equivalence relation. If R is reflexive, symmetric and transitive, then we call it an equivalence relation on A. This on A part sometimes is suppressed if it's understood what the set A is. You simply say R is an equivalence relation. Equivalence relation, not equivalent relation, okay? You can see these geometric examples. These examples are there in the text. Let T be the set of all triangles in the plane, and let R be the relation on T. So in this ordered pair, T1 and T2 are both some plane triangles, things like this, okay? And T1 is congruent to T2. That's the definition of the relation. If that happens, then we say that T1 and T2 are related by this relation R. Is it an equivalence relation? Is it reflexive? Let us see one by one the conditions. Is it reflexive? Reflexivity means every triangle should be congruent to itself. Yes, that is true. What about symmetry? If T1 is congruent to T2, obviously T2 is also congruent to T1, and this happens for any triangle. And that is why the relation is symmetric as well. And what about transitivity? Say you have three triangles, T1, this is T1, T2 and T3. T1 is congruent to T2 and T2 is congruent to T3. Then from school geometry, you know that T1 is also congruent to T3, and that is why this relation is transitive as well. So this is an equivalence relation. Equivalence relation on what? What is the set? The set of all triangles in the plane. But the next example is not an equivalence relation. At this stage, you may be thinking, what's the big deal about an equivalence relation? You won't really appreciate the need for this definition now itself, but it's coming. Not in this video, but in the other video that will come after this. There we will see why we need to even consider this notion of equivalence relations. In this next example, let us consider this. Let L be the set of all straight lines in the plane. Okay, so all kinds of lines, all of them taken together form the set L on a single plane. And let R be the relation on this set L defined like this. So R will relate two lines, two straight lines. But when? Precisely when they are perpendicular to each other. L1 is perpendicular to L2. Okay, so this is a legitimate relation. The relation of perpendicularity either relates two lines, for example, these two lines will be related to each other if they are perpendicular, but if they are like this or if they are parallel, then they are not related. Is this relation reflexive? Is a line perpendicular to itself? No, of course not. And that is why, and this is true and not true for any line in fact. So the relation is not reflexive. That alone is will tell you that the relation automatically is also not an equivalence relation. But let us see the other two conditions also. Is it symmetric though? If L1 is perpendicular to L2, is L2 also perpendicular to L1? Yes. So the relation is, although it's not reflexive, it is in fact symmetric. Is it transitive? If L1 is perpendicular to L2 and L2 is perpendicular to some other line L3, are L1 and L3 perpendicular? No, they are actually parallel. And that is why the relation fails to be transitive. So this is an example of a relation which is only symmetric, it's not reflexive or transitive. No transitivity. So it's not an equivalence relation either. Let us see this other example also, which does not really, which it's not about geometry but again about numbers. So the set on which it's a relation is this set, and the relation ordered pairs are there. Okay. Is this relation reflexive? You have to check whether A comma A belongs to R for every element A in the underlying set capital A. 1 comma 1, is it there? Yes. 2 comma 2? Yes. 3 comma 3? Yes. So that is why this is reflexive. What about symmetry? It is not symmetric. You can immediately see why. For example, 1 comma 2 belongs to R, but 2 comma 1 cannot be found here. So that is why it is not symmetric. Is it transitive? No, that also fails, because 1 comma 2 and 2 comma 3 belong to R, but 1 comma 3 cannot be found. It's not there in R. So it's not transitive. There are other examples also which are much more important than these preliminary examples. That, however, we will discuss in the next video. Anywhere you look in mathematics now, every now and then you will encounter equivalence relations, and in fact one equivalence relation you use all the time, which is equality. In fact, the idea of equivalence relations is a generalization of the idea of equality. Equality means literal identity, two things being the same. That is also an equivalence relation. Okay, so let me just end the video here itself. What do we have tomorrow? Yes, see, at this point I completely forget what we have. But I think after this, we are supposed to have either calculus or physics. Last week, due to that religious shouting, I was not able to start physics, but tomorrow I will. So tomorrow let us start with class 11 physics, with the first chapter, of course, units and measurements. So that's it. See you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.